and welcome to another video lecture in this series. Right now, I'm going to start in section 6.4, and that's a fairly long section on zero stability. It'll take me a few videos to get through it, so sit back and let's get started. Section 6.4 covers zero stability. What that means is that the global error in a method can be bounded in terms of the sum of all those one-step errors, and it can really have the same asymptotic behavior, that's as k goes to 0, as the local truncation error. And we've been focusing on local truncation error a lot. So zero stability is just taking that one step further. Now, there are several forms of stability, and we're going to see another one in chapter 7. So I want to start out with a bit of a motivating example in this first part of the lecture. So let's start out with a linear multi-step method, which is the two-step method you see defined there in equation 6.19 in your textbook. If you go through the local truncation error analysis, you'll see that the LTE looks like 5/2 k times u double prime at Tn plus an O of k squared. So we've talked about it many times. The local truncation error is big O of k, or first order accurate. But what that means is that you do have consistency, but it's not guaranteed to converge for all particular initial conditions and all problems. Now, here is a simple one that we're going to start on. So let's begin by considering what I'm going to call the trivial initial value problem. This means I put 0 on the right-hand side for f. I put 0 in as my initial condition. That's why we call it zero stability. All right, notice that means that the true solution is actually the zero function. Keep that in mind. Now, if I apply the method that was in equation 6.19 to this problem, it's going to have this form right there that you see in equation 6.21, just 0 on the right-hand side because my f is equal to 0. And then here is something to think about. So remember, I need two starting values. Let's call those u0 and u1. So suppose that I do that, and then I think about applying this method. Well, it turns out that then I'll get un equals 0 for all n if I just crank through what you see there in 6.21. However, what happens when I don't start right at 0? So the idea of zero stability is that maybe we don't have U1 exactly. Maybe there's some error. Maybe we have a guess. Maybe we have an approximation. So what if we don't have U1 equals 0? And what if the best we can do is something like U1 is equal to K? So it's still small. And it also goes to 0 as k goes to 0, but it's not 0, it's positive. What would that mean? All right, well, if we wanted convergence, what we would hope is that the nth time step of approximation would go to 0 as k goes to 0. But what we're going to find is that just even this small error in U1 will guarantee that this particular algorithm will blow up as I take more and more time steps. Okay, so here's something that we'll get used to, and I'll talk more about in the next video. For now, trust me on this, okay? Equation 6.21, whoops, there it is. That's also what we refer to as a difference equation, okay? And now that thing, you can solve that explicitly for UN in terms of U0 and U1. For now, Trust me on this, and it will make more sense in the next video, okay? I can express UN in terms of the first two iterates in this following way, all right? So that's what UN would be if you give me U0 and U1. I can tell you what it is. I did all the math. All right, so now keep track of the fact that the error at the nth time step is, what is it? Well, it is our approximation at the nth time step minus the true solution at the nth time step, which is just 0 in this case. So the error after n time steps is simply UN. All right. So now, what is that exactly? Well, I just told you in equation 6.22 what I worked it out to be. I'll show you how to do that soon. Well, I can see here that I can get a handle on this. And of course, that the thing that is sort of deriving things is this multiplier right here, this 2 to the n. Now remember, n is the number of time steps you're taking. And so as n increases, you're marching along in time. Well, as n increases, 2 to the n also gets large. So whatever error or whatever difference we have in U1 and U0 as a function, in this case, we're calling it K, as a function of K, as a function of n, 2 to the n is going to get very large, and eventually that thing is going to get much larger than the size of K. In particular, keep track or remember that the number of time steps you're taking is n, and then K is the size of the time step, and you're going to take enough of them to get you to your final time, capital T. Well, rewrite that equation just a little bit. That means as K goes to 0, capital N, the number of time steps you need to take, goes to infinity, right? That's a basic calculus idea. What that really means is that any small error up here, where we said it's of the size K, as K goes to 0, this other capital, this 2 to the n, right, is going to be behaving exactly the way capital N behaves that you see there. So that 2 to the n factor means that our difference equation is going to have a solution which blows up, gets unboundedly large. Okay. So now here's an observation I want you to make. 6.21 defines a difference equation that really corresponds to that polynomial P of zeta equals 0, that polynomial equation that we started looking at in section 5.9.2. So go back and check those polynomials, because what we're doing in 6.21 up here is simply looking at our polynomial forms in a certain way, and we're going to use them to essentially solve these difference equations and get some information about how the roots behave. That's the end of the first video in the series to cover section 6.4. Thanks for joining.